Okay, in the last video, I stopped at by the definition of discrete LTI system. Okay, discrete LTI, that means I told you discrete implies it's the sequence are x of n and y of n, they are all discrete. Then the output, input and the system. Okay, so as I said, linear time invariant, that means the system should be linear, that means it should be following the conditions of principle of superposition and principle of homogeneity. Then we say it is linear. Then the next is time invariant. It should be time invariant, it should not differ with the time, that means the delay or the response both must be equal, right? Yeah. Now the next thing what we have is, now we take the same discrete LTI system. Now we talk about the stability. Now before we go into the stability, we just have to write down what is the system function. The system function of this LTI. Now for that you consider y of n, which is output of LTI system. Obviously x of n is the input of the LTI system. Okay. Now this we consider impulse response. Okay, h of n. Now this output of LTI system is nothing but equal to convolution of input and the impulse response. So y of n is equal to x of n into h of n. This is the convolution of these two functions. Now next what we do it is, we take z transform on both the sides. When we take apply convolution theorem and we apply the z transform on both the sides, we get y of z is equal to x of z into h of z by convolution. Okay, so from this what we get is h of z is equal to y of z by x of z. So this x of z is the system function. Okay, now we consider this system function. Yeah. Now based on this system function, we talk about the stability of the system. Okay. Now let us consider, now the same h of z, now I am writing in terms of numerator and denominator. So let it be n of z by d of z. Okay. And this is how the numerator and denominator will be in terms of the z transform, y of z and x of z. So bn z power m plus bn minus 1 z power m minus 1 and so on. And this is the denominator d of z. Now consider the characteristic equation. We consider, take this d of z, we consider this characteristic equation and equate it to 0. So now our aim is to find the system to be stable, whether it is stable or not. So for that what we have is, we have the necessary and sufficient conditions. Now for finding out the stability, what we do it is, first we consider necessary condition. Now look at these necessary conditions. Now first one, d of 1 must be greater than 0. Take this, apply z is equal to 1 on both the sides. So d of 1, if it is greater than 0, this is the first condition. Second condition is minus 1 power n, d of minus 1 greater than 0. This n is what? Degree. Okay. So based on the degree, if it is a z cube, then this will be 3. If it is z square, it is 2. If it is z power 4, n is 4, in that way. So minus 1 to the power of n, d power minus 1 greater than 0. So if these two conditions are satisfied, then that means the necessary conditions are satisfied. Okay, if any one of them is not satisfied, then we cannot say the stability, we say it is unstable. But when they ask you about only the necessary condition, then you have to talk about these two. Okay, but to talk about stability of the function or of the system function, we have to even go with the sufficient conditions. So for sufficient conditions, actually we have different methods, but here we adopt one particular method, that is Jury's method or Jury's table, to find out whether the system is stable or not. So these two are the necessary conditions. Now next we go with the sufficient condition. Okay. So in next video, I'll talk about the sufficient conditions. I'll give you the table.